Students, I welcome you all. In Module 1, we are going to discuss Introduction to Stereochemistry. Stereochemistry is a branch of chemistry that focuses on the spatial arrangement of atoms in molecules and how this influences their physical and chemical properties. It plays a crucial role in understanding the behavior of molecules, especially in reactions of biological systems and material science. To represent a molecule as three-dimensional object, we need at least one carbon with sp3 hybridization. The below example represents 3D representation of a molecule, that is, a chiral center with four different groups. The center carbon here is sp3 hybridized. Unless the carbon having sp3 hybridization only can be expressed in three-dimensional view. This slide tells you the importance of stereochemistry. Most of the drugs are often composed of single stereoisomer of a compound. Among stereoisomers, one may have positive effects on the body and the other can have toxic effect. An example of such is a drug thalidomide, which was used during 1950s to suppress the morning sickness in pregnancy ladies. The drug was unfortunately in the initial prescribed as a mixture of stereoisomers, and while working, one stereomer showed controlling the morning sickness and the other stereoisomer caused serious birth defects. If you notice this picture, these are pictures of malformations due to maternal ingestion of thalidomide. The R enantiomer has sedative effects, while the S enantiomer of thalidomide is tetratogenic, means one can see malformations in the embryo itself. Coming to the classification of isomers. Isomers are the different compounds but having same molecular formula. If they are non-superimposable, they can be classified into two types: constitutional isomers or structural isomers, and another type is stereoisomers. Constitutional isomers differ in their connectivity of atoms. Stereoisomers differ in three-dimensional arrangement only, but molecules will have same bond connectivity. These stereomers can again be classified into two types: conformational isomers, configurational isomers. Conformational isomers are readily converted to each other through a CC bond rotation. Configurational isomers are generated only by breaking and making of bonds, but not simply through rotation through CC single bond. Configurational isomers are again classified into geometrical and optical isomers. Before entering into the classification, one should understand the basic terms in stereochemistry. Chirality. Chirality is a property of a molecule that makes it non-superimposable on its mirror image. Any chiral molecule, if it lacks an internal plane of symmetry and exists in two forms that are mirror images of each other but should be non-superimposable, those molecules we can call them chiral. In the below, we have given two molecules with a hand representation. One on each is of mirror images, but they are not superimposable. When a molecule can be called as achiral, when they are superimposable as well as they are mirror images to each other. Means the example I have shown here is symmetry in butterfly. It is a, if you could observe, a hypothetical plane which bisects the butterfly will result in equal mirror reflective halves, and they are superimposing one on another. Such molecules are achiral. Chiral is mirror images of each other, but they are not superimposable. Optical activity. It is the ability of a substance to rotate the plane of polarized light. This property is exhibited by compounds that are chiral. As I already mentioned, chiral molecule means they are non-superimposable mirror images. Substances that rotate plane of polarized light clockwise direction are called dextrorotatory, and those they rotate it anti-clockwise or counterclockwise, we call them levorotatory. An example is minus lactic acid. What is a chiral center? Chiral center is a specific atom, typically a carbon that is sp3 hybridized, bonded to 4 different groups or atoms. The presence of a chiral center often leads to chirality in a molecule. And a stereogenic center is any atom where swapping two groups attached to it results in different stereoisomers. For example, in the first case, a carbon is attached to 4 different groups COOH, CH3OHH. Interchange between two groups, that is H and OH, will result a new stereoisomer. Means the stereogenic center is the center by interchanging between two groups. If it results in a new stereoisomer, you can call that carbon center as stereogenic center. In example 2, I have taken a alkene where I interchange the groups on one carbon on the same carbon, that is hydrogen and methyl on interchanging their position will result trans isomer. Noting a point here, all chiral centers, but not all the stereogenic centers will be chiral centers. So coming to the classification, stereoisomers. Stereoisomers or diisomers that are having the same molecular formula but different spatial arrangement of their atoms, we call them stereoisomers. Under classification of stereoisomers, configuration isomerism refers to type of a stereoisomerism where molecules have the same molecular formula and the same connectivity of atoms but differ in the spatial arrangement of atoms or groups. They can be interconverted by breaking and making new covalent bonds. This rigidity makes the configurational isomerism significant in determining the physical, chemical and biological properties of molecules. Under configurational isomerism, optical isomers comes. They differ in the way they rotate the plane polarized light. This property arises due to the presence of a chiral center, an atom that is attached to 4 different groups. These optical isomerisms Isomers are of two types, enantiomers and diastereomers. Enantiomers are those optical isomers which are non-superimposable mirror images of each other. Chirality is necessary and sufficient condition for existence of enantiomers. They rotate the plane polarized light in either clockwise direction or in anti-clockwise direction. They always exist as discrete pairs. The plus and minus, that is, or lactic acid, D-lactic acid or L-lactic acid is one such example. Diastereomers or stereoisomers that are not mirror images of each other are called diastereomers. In the given examples A, B, C, D, AB is mirror images to each other, CD are mirror images to each other, and they are non-superimposable. Hence, we take them as an example of enantiomers. But A, with reference to C and D, we call them as diastereomers because they are non-mirror images. They are not mirror images. Coming to conformational isomers, these are the isomers that can be converted into one another by rotation around a single bond, that is between C-C. If you notice in the eclipsed anti and gauche conformations, C-C rotation in such a way, the three atoms on the first carbon will be exactly overlapped by the next carbon. Means the dihedral angle is of 0. On converting one molecule with an dihedral angle 180 degrees, one could attain anti or staggered form. Staggered form, we also call it as anti-form because the groups will be exactly opposite to each other on the CC single bond. In case of gauche, dihedral angle will be of 60 degrees. These molecules can be interconverted by rotating around the central carbon-carbon single bond. What are geometrical isomers? The isomerism that occur as a result of restricted rotation about a carbon-carbon double bond. We call it as geometrical isomerism or cis-trans isomerism. This restricted rotation occurs in compounds containing double bond C double bond C, C double bond N, N double bond N, any acyclic or cyclic structures containing restricted rotation due to steric hindrance. Below are the given examples for geometrical isomerism. Thank you for all.